Hello. Hello everyone. Today we will be discussing a technique named as TOPSIS. In multivariate analysis, you must have seen that the first principal component can be used as an index to summarize contribution from multiple variables. Okay. So TOPSIS is one more way of summarizing things from multivariate data. Basically, TOPSIS is part of what is known as MCDM. Okay, so TOPSIS is part of what is known as MCDM. MCDM stands for multi-criteria decision making. Multi-criteria decision making. So what does it mean? It means that when you have multiple criteria and you want to decide something by taking into consideration all of them, you need a way to combine the ranking. Okay, so TOPSIS is a way of doing that. Suppose you want to buy a cell phone. Okay, so what are the various ways in which you judge a cell phone, or what are the various criteria on the basis of which you judge a cell phone? First is perhaps how much RAM does it have? 4 GB, 6 GB, 8 GB. Then camera strength. In that also front you can have different for front camera and main camera. Then you may be interested in deciding, you may be interested in specific screen size. Okay, you may not want a bulky phone. You may be worried about the battery. You want a phone which doesn't need to be charged too often, and perhaps weight, and there are many other factors. Okay, so these are some of the factors, and of course price. So suppose you collect data on multiple phones, phone 1, phone 2, and so on, say phone 10, on all these parameters. So RAM, camera, maybe storage also, I don't know. Then screen size, battery, weight, price, etc. So you want a phone which ranks best, but it is impossible to get a phone which ranks best across all these categories, right? So what you want is you want a kind of a scoring system by which you can finally give a score to every phone based on all these things. And then whichever phone receives the highest score, you go with that phone. Okay. So when you are doing this exercise, what all factors come into mind? See, in PC also you can do that. So you can carry out a PC on the basis of these variables, but the problem is there is no guarantee that the indices in the first PC will have the desired sign. What do I mean by desired sign? So when we carried out PC earlier on some cricket data, there everything went well. Means we had collected data on batsmen, so the centuries, how many centuries they have scored, how many half centuries they have scored, how many sixes, how many fours, and total number of runs, and then strike rate. And we know that in this particular case, all these parameters are unit moving in the same direction. What do I mean by that? That for each of these variables, higher value is better. Correct? If centuries are higher, it is better. If number of 50s is higher, it is better. If strike rate is higher, it is better. Okay. So you can take some sort of weighted average, or if you carry out PCA and if the first PC has all of them with the same sign, then that can be used as an index. On the other hand, when you are talking of bowlers, you have number of wickets taken, then number of maiden overs, then number of runs given, etc. So you want wickets taken to be high, you want number of runs given per over, suppose. You want maiden overs to be high, but you want number of runs per over to be low. Okay. So if you carry out PCA, if automatically it turns out that these two have same sign and this has opposite sign, then it's good. Then you are lucky. But if it doesn't turn out that way, then PCA indexing won't help here. Okay. So TOPSIS, we will study in detail. So TOPSIS has an ability to accommodate such situation. So we know in the case of phone, I want RAM to be higher, front camera capacity to be higher, this to be higher, perhaps I want screen size to be lower, battery power to be higher, weight to be lower, and of course price to be lower. So there are some criteria for which lower the better, that is lower value is desired, and there are some criteria for which the higher value is better. Okay. In fact, there may be some criteria where higher or lower may not matter. You may want to stay within certain range. Okay. You may not want to go too low or too high. Okay. So TOPSIS has an ability to accommodate all these things. And then we can also assign different weights. For example, price may be much more important to me compared to screen size. I might be willing to compromise on screen size, but I may not be willing to compromise on price range. Okay. So while while devising the score, I would want to give more importance to price compared to screen size. So TOPSIS can actually do all these things. Okay. So what is TOPSIS and how does it work? Let me write the full form first. So I hope it is clear the scenario in which TOPSIS can be used. Okay. So TOPSIS stands for TOPSIS. So TOPSIS stands for Technique for Order of Preference. Technique for Order of Preference by similarity to ideal solution. By similarity to ideal solution. What does it mean? Okay, so what is the first step? What are the steps involved in TOPSIS? First step is we identify the criteria. So what are the criteria? Criteria are the variables. So for example, in the case of phone, my criteria were RAM, then screen size, then camera and battery and so on. Okay. Then the second step is normalizing the data. Because as you can see, my criteria will have different range and I don't want a criterion to be considered as important just because it has wider range. For example, in the case of the criteria that we discussed for the phone, price will be 5-digit number, whereas RAM will be a single digit number. Camera power will be at most 2 or 3-digit number and so on. Okay, so when I compute differences between the price, they will of course be very high. Okay, and we don't want those differences to increase the weight of the price variable. Hence, we normalize all continuous variables to generally between 0 1 range. Of course, you can use other type of scaling like our z-score computation, means converting everything to more or less plus or minus 3, etc. But generally, we do min-max scaling and we get range between 0 1. Min-max scaling means every value is converted into x minus minimum of x divided by maximum of x minus minimum of x, so that every value stays between 0 1. Okay. Then we decide which criteria are, we decide relative importance of various criteria. For example, here suppose price is 5 times more important compared to screen size. Then I give weight 5 for the price and screen size gets weight 1. Then weight of the phone also gets weight 1. Camera perhaps gets weight 3. Battery perhaps gets weight 2 and so on. Okay, so we assign relative weights to different criteria. Now we have to construct what is known as ideal solution. Okay, what is ideal solution? So ideal solution, so for price, minimum value in the current data set would be considered as ideal solution. On the other hand, for screen size, I might have a fixed value in my mind. I don't want a very small screen and I don't want a very large screen. So perhaps something like 5.5 is the ideal value for me. Then for weight again, minimum in that range. For camera, whatever is maximum in that range. For battery, whatever is maximum. These may be my ideal values. Okay. So we construct ideal solution, and now what we have to do? We have to compute distance for each value or each phone from the ideal solution. Okay. So if it is continuous data, we can simply compute Euclidean distance, and if it's categorical data, then we may have to compute binary type of distance, okay, trivial distance. So we compute for every phone, we compute Euclidean distance between its value and the ideal value. Okay, now this is distance, and then we have to convert this distance to similarity. So we compute what is called as closeness coefficient. Okay, what is a closeness coefficient? Closeness coefficient is computed to decide which phone is most close to the ideal solution with respect to individual variable. So how we do that? We compute distance of individual phone to ideal solution. Of course, right now we are talking in terms of single variable, for example, say camera. And then we divide it by distances of all the phones. So distance of phone I to ideal solution and sum over I going from 1 to 10. Then what will happen? If distance of the current phone is very much less compared to distance of the other phones, then I will get a very small value. Okay. So lower value of closeness coefficient is actually better. Correct? Lower value is better here. And now we have to rank the phones based on their closeness. So the phone which gets smallest closeness value gets highest rank with respect to that variable. Okay, and these closeness coefficients, we can take something like weighted average of these closeness coefficient across all variables and then give the final ranking. Okay, so we get a final score where that score is kind of an indicator of similarity to the ideal solution. The final score is actually adjusted to make sure that it is intuitive in the sense, um, higher score would mean a better ranked object, okay, or a better ranked phone. Okay, so you also have a facility to give what is known as negative ideal solution. Okay, so negative ideal solution means you can also see how far or how close it is from the other end, other extreme. Okay, that can also be taken into consideration. So this is one of the very important tools, and R has a direct command for TOPSIS. There is a package called TOPSIS. In fact, it is available in multiple packages, but the package TOPSIS gives a single command TOPSIS which can be directly applied to get scores, and those scores can then be used for ranking objects based on multiple criteria. And hence, as I said in the beginning, this is known as MCDM, multi-criteria decision making. Okay, so I will upload R file also, R file or markdown file where this will be applied, and then you can try to use it for some data set. Okay, let me stop here. Thank you.